Okay, we're now continuing from page 16 of the complex number booklet. We're looking at the complex number plane. Now, complex numbers cannot be represented on an ordinary number line, as they cannot be ordered like real numbers. However, they can be represented in a plane, in an xy plane. So the complex number z equals x plus yi can be represented by the point P, say a point P, on a number plane with coordinates x, y. Now, this representation of the complex number field is called the complex number plane, or an Argand diagram, or it's also called the z-plane. So the image points of real numbers, so we put the real numbers x on the x-axis, and so therefore we say that this x-axis here is the real axis, and the pure imaginary numbers appear on the y-axis. So therefore the y-axis, this axis here, is called the imaginary axis. So we've got x-axis is the real axis and the y-axis is the imaginary axis. Now, we know that I squared equals -1. So therefore, we're going to do a bit more of this later, but I'll just briefly mention it now. So therefore, if we multiply a number by -1, you're going to see a bit later when we do it that it's going to be a rotation through 180 degrees about the origin. And if we multiply a number by I, it's going to be rotation of 90 degrees. Okay, so now you'll see this a little bit later on in the book, but just notice that the real and imaginary axes are at 90 degrees to each other. And a complex number, we can define it as a point. So we can have, for example, the point with a dot P, but also the complex numbers can also be represented by vectors, like the vector OP with an arrow, starts at O, finishes at P with an arrow there, but we'll be looking more at that later as well, where the tail here is at O and the tip is at P. Don't worry too much about that. We'll be doing a whole section on that. What we're going to just do here first is just plot some points on the complex number plane, or the z-plane, or as it's also called, the Argand plane. So just some brief, some simple plotting here. If we want to plot the complex numbers 5 plus 2i, 5 is the real bit, 2 is the imaginary bit. So here is 5 plus 2i. So this is 5 plus 2i. -3 plus 4i, just like plotting normal points on the number plane. -3 is the real bit, 4i is the imaginary bit. So this point up here is -3 plus 4i. -4 minus 3i, -4 minus 3i would be down here. And the last point, actually no, there's more than the last point, 2 minus 4i. 2 is the real bit, minus 4i is the imaginary part, so 2 minus 4i is down there. And 2, just the number 2, there's no imaginary part here, it's just the real bit, so that is the point 2. And minus 2i, that is purely on the imaginary axis, and this point here is minus 2i. Okay, so note that if z equals x plus yi is real, as in, for example, 2 is real, okay, then there will be no y component. Then y will equal 0. So if y is 0, you've only got the real component, okay? And the point P will lie on the x-axis, okay? So if y here is 0, then your z equals x, so it's just a real value there. However, if z equals x plus yi is purely imaginary, or just imaginary, then it'll just have the yi component and not the x component, and so therefore x would equal 0, and the point therefore would lie on the y-axis. Just noting here that x is for the real and y is imaginary, and we can even write it as yi. Okay, now What we're going to do is we're going to, in example 2 here, we're going to plot z equals 3 plus 2i. So if z equals 3 plus 2i, we want to plot z and bar z, z bar on the argand diagram. Now we know that z bar is the complex conjugate of 3 plus 2i. So z bar is 3 minus 2i. So let's plot z. 3 plus 2i is here. That's z, which is 3 plus 2i. And if I plot the complex conjugate of z, which is z bar, which is 3 minus 2i, so this here is z bar, which is 3 minus 2i, you will notice that, yes, they're a pair of complex conjugates, but they're reflections in the real axis x. Okay, so this point is z bar is a reflection of z in the x-axis. The reason is that the real parts of complex numbers are the same, of the complex conjugates are the same, but the imaginary parts have changed from positive here to negative there. Okay, so we've got 3 plus 2i, 3 minus 2i. Okay, now we're looking at the sum of complex numbers. Now, remember when we were adding before, if we look at the sum of two complex numbers, a plus bi plus c plus di, we add the real components and we add the imaginary components. I need an I here. So a plus c plus b plus d times I, okay? So on the argand plane, the sum of the complex numbers, the real component would be whatever a plus c is, and the imaginary component would be whatever b plus d is. Now, there are two ways that vectors can be added. Okay, now we know that, for example, the point P is, say, a plus bi, but we can put it as a point or we can draw it as a vector from O to P. Okay, so we call the point P vector OP, and we call the point Q over here vector OQ. Okay, or just vector Q, but same. All right, Now there are two ways that you can add the vectors OP and OQ, okay, or vectors P and Q. Now, first what we're going to do, the first method is called the parallelogram method. So what we do, we want to do vector, what we want to do is P plus Q. We're trying to add these two complex numbers, P and Q. So what we're going to be doing is adding vector P to vector Q. So here is vector P or vector OP. And here is vector OQ, because if C plus DI is, say, down there. So what we do, we actually draw a parallelogram up from here. So we start with this and that's vector OP. There's vector OQ. What we do, we draw a parallel dotted line here, parallel to OP, and we do a parallel dotted line here, parallel to OQ, and we have our new point there. And this here in the middle, from O to this point here, is the vector of P plus Q. So this vector here is actually the addition of vector OP and OQ. Okay, so we've got vector OP there, we've got vector OQ here. So we translate vector Q until its tail, so the two tails meet here at O. Then we construct the parallelogram. Then we draw along the diagonal, basically here to the other corner of the parallelogram, and this will be P plus Q. Now we're going to do this down here, okay? So you might find this a bit confusing here. The other way you'll do it, and some of you are physics students, you just do it like you would add normal vectors in physics. Here is vector P or vector OP. And so we want to use the tip to tail method here. So vector OP, and there's vector Q or OQ. We add that on, and we know that we started there and we finished here. So therefore the resultant vector P plus Q is from this starting point here to this finishing point there. So what we're going to do here is we're going to use both methods, and we're going to add the complex numbers 4 plus 2i and 1 plus 3i using both methods. Now the first method I'm going to use is the parallelogram method. So parallelogram method. And here I'm going to use the tip to tail method, the physics method. Okay, so parallelogram method, let's start with that first. I'm just going to change colors here. So the first vector or point is 4 plus 2i. So we've got 4 plus 2i. So what I'm going to do here is draw, instead of just putting 4 plus 2i, I'm going to draw the vector here from the origin to this. Okay, that's my first vector. Okay, and the second one, so this point here is z1. Okay, 4 plus 2i. The second vector is 1 plus 3i. So I go 1 plus 3i. There's vector 2. So I'll call this z2. Now I need to draw a parallelogram. So I want to use the parallelogram to add these two vectors. So just noticing, to go from here to there, I go up 2 across 4. So from here, so I need to be parallel to that. So this line that I'm drawing here needs to be parallel to that. So from this point, I should go up 2 across 1, 2, 3, 4, and I'll draw a dotted line. And notice this vector is up 3 across 1. So from here to there, it is across 3 up 1. So basically, I'm just drawing a parallelogram. I just need to make sure that this line is parallel to that one. This first vector, sorry, is parallel to that. And once I've drawn the parallelogram up, then the resultant, the diagonal here, across there, this resultant point here is z1 plus z2, or therefore, now if we look at this, so I've got z1 plus z2 is basically here, this point here, which looks to be 5 plus 5i. Now let's add these two together. So z1 plus z2 is 4 plus 2i plus 1 plus 3i, which is 4 plus 1 plus 2i plus 3i, which is 5 plus 5i, which is where this resultant point is, or where our resultant vector ends. Okay, so now let's look at the tip to tail method. So I'm going to draw the first vector first, which is z1, which is 4 plus 2i. So I'm going to do that first. So I'll call this z1. Now, instead of drawing this second one from the origin, it's 1 plus 3i. So it's 1 plus 3i. I'm going to move that, I'm going to draw that same thing here at the tail. So I've got tip to tail. So the tip of the first one goes to the tail of the second one. So I know 1 plus 3i is here. Okay, I'll just do that really lightly. Right, that's my 1 plus 3i there. But I'm not going to leave it there. I'm going to move it so that it's at the tail here. So that it's at the tip, sorry. So 3 up, 1 across to get that same, so that's parallel to that, but move it here. So here is that second vector. So I want to add these two vectors. So as you do in physics, draw the first one, then draw the second vector at the tip of the first vector. And so therefore the resultant vector is here. So this is my resultant vector. So this resultant vector, or this point, will be z1 plus z2. Okay? So again, you would get the same thing here. z1 plus z2, if we add them together, is 5 plus 5i. Reading it from the diagram or adding them together as you have been doing previously. So therefore, the addition of complex numbers, the way we were doing it before, does correspond with the addition of corresponding vectors in the Argand diagram. Now, subtraction of complex numbers. So let's look at this. Remember that subtraction is defined as the additive inverse. So when you want to subtract complex numbers, so for example, so I'm going to draw them here. So z1 is 4 plus 2i. So here is 4 plus 2i. That's z1. Okay, 4 plus 2i. That's z1. And Z2 is 1 plus 3i. Here's Z2. I'm just going to do it in red. Oh no, I'll do it in this color. This point here is, what have we got? 1 plus 3i. Okay, but we know that when we subtract, so if I want to do Z1 minus Z2, subtraction is defined as the additive inverse. So it's Z1 plus negative Z2. Okay, so what is the negative of 1 plus 3i? It's negative 1 minus 3i. So negative 1 minus 3i is down here. So I'm going to draw the vectors, actually. I'm going to label them on the arrows. So if this is Z1, this is Z2, this is minus Z2 down here. Okay, so now I want to add Z1 to minus Z2, so I use my parallelogram method. So just looking at this sort of direction here, it's down 3 across 1, so down 3 across 1, do my dotted line, and then this one will just form up my parallelogram. So I've got a vector going out there, a vector going out there. So with the parallelogram method, my resultant vector is here. So this resultant vector here, I'll just put an arrow to it, is Z1 minus Z2, this resultant vector here. Okay, now let me just use subtraction of complex numbers to see what Z1 minus Z2 is. So Z1 minus Z2 is 4 plus 2i minus 1 plus 3i, which is 4 plus 2i minus 1 minus 3i, which is 3 minus i. And is that where we've ended up here? And we have. This resultant point is 3 minus I. So that's subtracting complex numbers using the parallelogram method. So this is the parallelogram method. And now we're going to look at the tail to tip method. So let's look at our first vector, 4 plus 2i. So I can either write 4 plus 2i or even z1, it doesn't matter, but I'll put z1 here. And I've got 1 plus 3i. So remember, that is 1 plus 3i, but I don't want 1 plus 3i. I want minus 1 minus 3i. So this is minus 1 minus 3i. So if this is Z1, this bit is Z2, this is minus Z2. So if I want to use my tail to tip method, there's my first vector. I add my second vector on the end here. So here's my second vector. And then therefore, so first vector, second vector, I start here, I finish here. So therefore my resultant vector is from the start to the finish, which is this. So this point down here is 3 minus I, and that vector there is Z1 minus Z2, and that's using the tail to tip method, okay? And as I was saying before, the subtraction of complex numbers corresponds with the subtraction of, so as we can see, when you use the parallelogram method, you end up, at 3 minus I. And when you use the tail to tip method, you end up at 3 minus I, and that is identical to just subtracting complex numbers as we were earlier, okay? So the subtraction of complex numbers corresponds with the subtraction of the complex vectors in the arcane diagram. So just another example here. So if Z1 is 3 minus 2i, so I'm just going to do that. So I've got 3 minus 2i. So that's 3, that's minus 2. So if Z1 equals 3 minus 2i, well, I'm not going to put it there yet. So that's my 3 minus 2i. Actually, I will. So that's Z1. And if Z2 is negative 1 plus 4i, that would be this vector here, so Z2, okay? So if Z1 and Z2 show on an Argand diagram the vectors OP, OQ, so show on an Argand diagram the vectors OP and OQ, so this is the origin, so this would be point P because that's OP, okay? So this is O, so this is OP, and OQ, so this is the point Q, okay? So OP and OQ, and OC represents Z1 times Z2. I think that's a little mistake there. I just got to check that. Actually, no, it is correct. So if Z1 is 3 minus 2i and Z2 is minus 1 plus 4i, show on an Argand diagram the vectors OP, OQ, and OC, which represent Z1, Z2, and Z1 plus Z2. So vector OP is Z1, vector OQ is Z2, and we have to represent Z1 plus Z2. So we can either use the parallelogram method or the tail to tip method. I'll use the parallelogram method, so need to draw up a parallelogram, and it looks like across 3 down 2, so across 3 down 2 just to get this angle correct. And here up 4 across 1, just checking up 4 across 1, yes, that's correct. So there's my parallelogram. I have an arrow out like that, an arrow like that, and here is my resulting vector. And if OC, so this is C, represents this vector here is Z1 plus Z2. Okay, so that vector there in red, this is just an arrow labeling it, is Z1 plus Z2. So this is vector Z, this vector OP represents Z1. This vector OQ represents Z2, and Z1 plus Z2 is represented by vector OC. Okay, so it says, so the vector, so OC represents Z1 plus Z2, and the question here is to name a vector which represents Z1 minus Z2. So I need Z1 minus Z2. So let's just have a look. What we need to do is do Z1 minus Z2. So that's plus Z2, minus Z2 goes this way. So let's just look at what Z2. Z2 is minus 1 plus 4i. So minus Z2 is 1 minus 4i. So 1 minus 4i. So I'll just do this in a different color. Okay. So Z1, sorry, minus Z2. So this one here in red, or I'll do it here in purple as well. This is minus Z2, okay? And if I do the resultant parallelogram across 3 down 2, across 3 down 2, so if I do another resultant parallelogram here, then the resultant vector goes down like that. Now, if I do Z1 minus Z2, so if I do Z1 minus Z2, I've got 3 minus 2i minus negative 1 plus 4i, which is 3 minus 2i plus 1 minus 4i, which is 4 minus 6i, and that is where I have ended up here, 4 minus 6i, okay? Now, if I look at if we look at this here, that is the complex number, Z1 minus Z2, okay? So it's an arrow from there down to here, but a vector that would be the same, in the same direction as that, this vector from Q to P, so the vector QP also represents Z1 minus Z2. The reason is it's actually the same vector as this from O to this point here. Now this point here doesn't have It doesn't have a point, all right? Like this is P, this is C, this is Q. In this little example here, we've got no definition here for Z1 minus Z2. So this vector is like 4 across, 6 down. Well, so is this vector here from Q to P. It will be 4 across, 6 down as well. So this vector here that I'm doing dotted, that dotted vector, QP, represents Z1 minus Z2. So notice one diagonal here is Z1 plus Z2, and the other diagonal, so this short diagonal OC, is Z1 plus Z2, and this other diagonal QP is Z1 minus Z2. So it's basically the other diagonal. Okay, I'm just going to do the top little bit of this page and stop the video and restart here for polar form of a complex number. So multiplication of a complex number by I. So I was talking about this a little bit before and saying how multiplying by I is a rotation of 90 degrees, but we're actually going to show it here. So if Z equals 4 plus 3I, show the following on the complex plane, IZ. So that is I times 4 plus 3I, which is 4I plus 3I squared, which is negative 3 plus 4I, because I squared is negative 1. So let's just plot Z, 4 plus 3I, that's Z, which is 4 plus 3I. Let's plot IZ, which is negative 3 plus 4I, which is negative 3 plus 4I. Now, I'm going to look at I squared Z. Now, we know I squared is negative 1. So that's negative 1 times Z, which is negative 1 times 4 plus 3I, which is negative 4 minus 3I. And if we plot that, negative 4 minus 3I, negative 4 minus 3I is down here. And that's that's I squared Z, which is negative 4 minus 3I, okay? And the last, so I cubed Z, that is I times I squared Z, which will be I times negative 4 minus 3I, because I squared Z is our answer here. So we get negative 4I minus 3I squared, which is 3 minus 4I. So 3 minus 4I, that is I cubed Z, which is 3 minus 4I. So notice that you'll see why it's a rotation about a quarter turn about O in a minute. All right, so what I'm going to do, I'm just going to join these and these. And if you see here, these are right angles. Okay, and if you use Pythagoras' theorem, this is 4 across 3 up. The length of this is 5. Look here, so 4 across 3 up. Look, 4, 3. See, I'm coming across the axis 4 and then out 3. Here I'm going 4, out 3. 4, out 3, and 4, out 3. Basically, it's like I'm spinning this around. It's like I'm going 4, 3, 4, 3, 4, 3, 4, 3. So we can see that Z, going from Z, sorry, I don't know why I wrote negative Z, sorry. That's a mistake. That's IZ. So from Z to IZ, that's a quarter turn, about 90 degrees. And from IZ to I squared Z, that's another quarter turn, about 90 degrees. So we're turning 90 degrees. And then from I squared Z to I cubed Z, another quarter turn, 90 degrees. And from I cubed Z, let's just look at I to the power of 4Z, that's I squared times Z, which is negative 1 times negative 1, times Z, which is just Z, which is just 4 plus 3I. So this point here is I to the power of 4Z, back to where we started, okay? So multiplication of a complex number by I is equivalent to a quarter turn about the origin. origin, which is a 90-degree rotation, and multiplication by I squared. So if we look at Z, and here I've got I squared Z, that is just a rotation. That's like point symmetry. It's a rotation by 180 degrees. Okay, that's the end of this video. I'm going to continue from here, polar form of a complex number.